All right, so if you've done any serious turning, you know that moment, right?
Yeah.
You've got this long, maybe heavy shaft cinched up in the chuck, and your eye just goes straight to the tailstock. You need that center support to keep everything rigid, true, and stable during the cut.
Yeah, and it feels like such a simple decision. You just grab the nearest center, jam it in, and you're ready to go.
But it's not.
It's not. That choice, and it feels like a really minor setup detail, it basically dictates the ultimate limit of what you can do.
Mm.
You grab the wrong center, and you are on a fast track to destroying your surface finish, dealing with some catastrophic thermal distortion, or worst of all, just instantly scrapping a really expensive part.
Exactly. And that's what we're doing today. We are diving deep into the difference between the dead center and the live center. This isn't just about a piece of hardware. This represents really the ultimate trade-off in machining physics: speed versus absolute micron-level precision. Our mission today is to cut through all the noise and just shortcut your knowledge on this essential component. We're going to explore the high-stakes engineering that separates these two tools.
And, for anyone tuning in who just needs the bottom line, here's the core rule you should probably just internalize right now.
Go for it.
You choose a live center for general CNC turning, high-speed stuff, production volume. The goal there is to eliminate friction and heat. That's it.
And on the flip side, you must choose a dead center for jobs where runout has to be, absolutely near zero. Think specialized grinding or that really low-speed, high-precision finishing.
Right. If you need perfection and concentricity, you just have to accept the risk that comes with friction.
It's efficiency versus perfection.
It really is. And the mistakes, they're incredibly costly. We see it all the time. Operators burning out dead centers because they're running them way, way too fast. They just melt the hardened tip in minutes.
Or the other way around. Trying to hit impossible tolerances with, like, a cheap or worn-out live center, one that has too much bearing clearance,
And it introduces just enough wobble to ruin a critical bore or a shoulder length. Yeah.
And avoiding those expensive mistakes is what this whole deep dive is about. Okay, so let's unpack this. Let's start with the physical structures that create these trade-offs.
Okay, so when you hold them both in your hand, the difference is visually obvious. One spins, one is just solid.
Right.
But the real engineering question is, how does that mechanical difference fundamentally alter the physics of your cut?
Let's start with the dead center. Break down the anatomy for us.
It is the essence of simplicity. It's a solid, single piece of intensely hardened steel ground to a very precise point.
Okay.
It's fixed rigidly in the tailstock taper. It does not move. It is stationary.
So the workpiece spins against that fixed point.
Exactly. We call that static contact.
So what's the immediate massive benefit of that simplicity? If a high-precision bearing assembly can hold tolerances down to a micron, how can a fixed piece of steel possibly be better?
Because there are zero moving parts.
Ah.
No balls, no rollers, no races, no oil film, no thermal variance from bearing friction, nothing.
Okay.
By eliminating all that internal movement, you guarantee the highest possible positioning accuracy and rigidity. You get this unparalleled concentricity because that point of contact is absolutely fixed in space.
But the drawback is the friction. Metal on metal.
High friction. And it needs constant lubrication under extreme pressure. We'll get into that.
All right, so now let's switch to the live center. You're looking at something that is, fundamentally more complex.
Oh, yeah. It's not one piece. It's a whole assembly.
Right. You've got that front cone that touches the part, but that cone is mounted on this whole internal array of rolling bearings inside the main housing.
And its motion is the complete opposite. The front cone rotates synchronously with the workpiece.
So the friction point moves from the tip of the center to inside the center's own bearings.
Precisely.
And I know the quality centers, they use a really complex internal setup, maybe a thrust bearing and multiple needle bearings, all designed to handle both the weight and the tailstock pressure at the same time.
That bearing array is the magic. Because the tip is spinning with the part, the sliding friction between the center and the workpiece is practically zero.
Which is the game changer for high speeds.
It's everything for high-speed cutting. It completely eliminates that friction and heat problem right at the contact point.
But there it is. There's the trade-off. Because to get that rotational freedom, you need clearances. Even in a super high-precision bearing, you have clearance.
You have to.
And that introduces a small but measurable amount of radial runout, a tiny wobble.
Precisely. And we are talking clearances measured in the low micron range, but that is enough to affect your rotational accuracy.
Which is why we generally reserve them for roughing or semi-finishing.
Exactly. Jobs where your speed and your material removal rate are, frankly, more critical than hitting the absolute tightest concentricity tolerances.
So to synthesize this then, we have a solid stationary center for ultimate rigidity and perfect concentricity
Right. Static contact.
versus a rotating bearing-driven center for high-speed, low-friction operation, dynamic contact.
That's the summary. Dead is stationary. It excels at precision, but only at low to medium RPMs. Live rotates, it's optimized for high speeds and, nonstop CNC production.
And you're just trading a tiny bit of that theoretical accuracy for a massive gain in efficiency.
Massive gain, yes.
Okay, so that rigidity of the dead center, the very feature that gives you the precision, that leads us right into its primary paradox. It gives you accuracy, but it creates this kind of self-destruct mechanism through friction and heat.
It does. It's the rigidity risk.
So let's dive into the high stakes of high friction.
When you have two pieces of metal rubbing against each other under the immense pressure from a locked tailstock, the friction generates heat fast.
And if you overlook that heat.
You will scrap that workpiece extremely quickly.
And the really fascinating physics here is all about thermal expansion. The moment that part heats up, from the tool and from the center, the metal literally tries to grow lengthwise.
It does, and the scale of this growth can really surprise people. On a long, slender shaft, the thermal expansion can be significant. We're talking maybe zero point 0.4 to 0.6 millimeters.
Wow.
And the problem is the tailstock is locked. It's fixed. So the expanding part has nowhere to go. It just pushes harder and harder against that fixed center point.
And that's the feedback loop. That's what the sources call the cycle of failure.
Exactly. The part rotates, friction generates heat,
The metal expands,
which leads to exponentially more pressure on the center.
which creates even more friction and then even more heat.
It is a runaway train.
Yeah.
And if you don't manage to stop that loop, the consequences are immediate and disastrous.
Like what? What's the worst that can happen?
Galling. The heat and pressure can cause the two surfaces to instantly weld themselves together. The pressure can also get so immense that a slender shaft being squeezed between the headstock and tailstock, it will actually start to bow or distort.
I remember reading about the smell when a dead center fails from heat. It's this sharp, burnt metallic smell, and you know instantly you vaporized the tip of a center that should have lasted for years.
And in worst case, the combined force can just cause the part to pop right out of the machine, which is a huge safety hazard.
So how do you manage this?
The lubrication requirements are extreme.
Yeah.
You can't use regular cutting oil. It just spins off instantly. You have to use a dedicated high-pressure lubricant, something like molybdenum disulfide grease.
Stuff designed to survive enormous shear forces.
Right. And you have to keep the RPMs low. You absolutely cannot run a dead center at 3,000 RPM. And even then, the operator has to babysit the process.
Frequent stops, backing off the pressure, re-lubricating.
Exactly. To nurse the job safely to completion. It's a high-maintenance precision.
Which brings us right to why modern manufacturing, especially high-throughput CNC, just defaults to the live center almost every time.
Yeah, CNC machines are designed to run fast for hours, often unattended. A solid center just can't handle that scenario without risk.
The live center solves all those high-maintenance problems.
All of them, at once. The first big reason is thermal consistency. Since it rotates with the part, it just stops that friction buildup. The part doesn't grow lengthwise.
So for long production batches, your shoulder lengths stay consistent.
Perfectly consistent makes the whole process predictable.
And the second reason is just pure speed, which is an economic driver.
It is. Modern CNC turning uses high-performance coated carbide inserts. They're engineered to perform best at really high surface speeds. A dead center puts a hard limit on your RPM.
Forcing you to underperform your expensive tooling.
That's the critical point. If you try to run at the optimal speed for your carbide inserts with a dead center, you will destroy that center tip in minutes. The live center just lets the operator run at maximum efficiency, maximum profitability.
And there's a third advantage, one that often gets overlooked, that's related to post-processing.
The center hole.
Exactly. If you're turning a shaft that's then going to a cylindrical grinder, that center hole is your critical registration point for the second operation.
Wow.
The live center preserves it.
That preservation is vital for quality control. Since it uses rolling contact bearings, it doesn't rub or ovalize or score the surface of the center hole,
Keeping it accurate for whatever comes next.
which is often a requirement for ISO standards and high tolerance work.
And finally, a great insight, especially for long, slender shafts. The bearing structure of the live center actually helps dampen vibration.
Yes, it acts as a kind of mechanical shock absorber.
Mm.
The internal bearing setup absorbs some of the cutting harmonics, especially when you're working far from the chuck.
Which improves stability and gives you a better surface finish.
A better surface finish,
Yeah.
even at higher speeds, yeah.
So we've pretty much established the live center as the champion of speed, efficiency, and consistency. But its complexity is also its weakness.
It is.
Because it relies on those bearings, it has a definite Achilles heel. Load limits. You can't just ignore the manufacturer's specs.
That's right. A live center is only as strong as its smallest bearing. If you overload it, you're looking at catastrophic, non-repairable failure.
I often hear people talk about tailstock pressure as the main threat, the axial load. But why is the radial load, just the simple weight of the part pushing down, a separate and often bigger threat?
It's because standard live centers are designed with substantial axial thrust bearings to handle that inward force. They're good at that.
Okay.
But the radial load, the downward weight, which gets amplified by cutting forces, that puts tremendous uneven stress on the smaller needle and roller bearings that manage the rotational stability.
So what happens inside when a small center is forced to hold a shaft that's way over its weight rating?
The internal bearings suffer massive pressure concentration. The rollers, or balls, literally press into the steel races. It's a process called Brinelling.
Brinelling.
It's like tapping a small punch into soft metal. You create these tiny, permanent dents in the race where the rollers were sitting under load.
And that damage is permanent.
It's permanent. Once Brinelling starts, that center is compromised. The bearings will overheat, they'll degrade, and then eventually they'll seize up.
And that's where the safety and scrap risk just goes through the roof.
Oh yeah, if that internal bearing assembly seizes while your lathe is spinning at, say, 1500 RPM, the center tip instantly stops dead. But the workpiece keeps spinning.
Oh, that's bad.
It instantly gouges the center hole of your part, destroys that registration surface, and it almost always breaks the cutting tool in the process. It's instant scrap.
So there's some real engineering here that gives a crucial kind of non-intuitive insight. We hear about the L10 life factor for bearings. What does that tell us about managing these loads?
The L10 factor is the calculation engineers use to predict the fatigue life of a bearing. And the crucial takeaway for the listener is that bearing life decreases exponentially, not linearly.
So if you double the load, you don't just cut the life in half.
No, you reduce it significantly more than half, often to just a fraction of its original rating.
So give me a practical example. A 1-hour job. I use a live center rated for 1,000 pounds, but I push it with 1,500 pounds, a 50% overload. It's not going to fail in 40 minutes.
That's going to fail much, much faster. Based on the cubic relationship in L10 calculations, that 50% overload could reduce the bearing's life to less than 20% of its rating.
Wow.
So instead of 40 minutes, you might see a failure in under 12 minutes of runtime. The moment you go past that limit, the risk just skyrockets.
That makes the recommendation for anyone dealing with heavy material totally clear.
Always check the manufacturer's max radial weight rating before you load the part. If you're handling heavy work massive rollers, long, thick shafts, it is dramatically cheaper and safer to invest in a heavy-duty center.
Like those bullnose styles with extra rows of bearings.
Exactly. It's cheaper than risking a seizure and scrapping a 2-ton piece of steel.
So what does this all mean for the person at the machine right now trying to decide what to grab?
It means the distinction is foundational. Live centers are the absolute standard for high-speed, efficient CNC production. They eliminate thermal risk, and they manage consistent batches.
And dead centers.
Dead centers remain the king of accuracy for grinding and low-speed work, where minimizing runout is the highest priority, and you're willing to manage all the risks and lubrication demands by hand.
So the choice is purely about what you prioritize. Speed and efficiency or extreme absolute precision.
That's the whole trade-off.
And what's really fascinating here is how a decision that seems so simple fixed tip or moving bearing forces you to manage such advanced engineering concepts just to turn a perfect shaft.
It's true.
You have to handle thermal dynamics, worry about high-pressure lubrication, and account for complex physics like the L10 life factor and exponential failure rates.
It's all that hidden complexity right there in the heart of these simple tools. We spend so much time focused on the cutting tool itself, we forget the silent component that's holding the whole operation true.
It is. So we'll leave you with this final provocative thought. What other simple, overlooked components in your field, those tools you grab every day without a second thought, what other tools conceal such complex, high-stakes trade-offs between two entirely different worlds of engineering? Something to consider the next time you step up to the machine and check your tailstock.